Hello everyone, I'm Zhichen Sun from Peking University. Today I would like to introduce our work, Exploring Orthogonality in Open World Object Detection. Open World Object Detection is a problem setting that studies object detection in an evolving world that continuously adds new object classes to the training data. To achieve this, it follows a two-step iterative process. First, the detector identifies objects of both seen and unseen classes. Then, those objects of unseen classes are provided to a human annotator to curate new training data. And in the second step, the detector incrementally recognizes those newly annotated objects. While this setting allows the detector to operate in an open world, it poses significant challenges to predict objectness using class-agnostic information. However, existing methods usually over-rely on class information to predict objectness, which results in less generalizable detection. We are thus motivated to promote more class-independent detection results by enforcing orthogonality between the decision boundaries of objectness and class predictions. This is the overview of our method. We start with a fast RCN-based base model, and enforce orthogonality in both its feature space and prediction space. And during incremental learning of new object classes, we continuously calibrate the feature orthogonality. First, to enforce orthogonality in the feature space, we project the features of each object proposal into two orthogonal components of magnitude and direction, where the objectness prediction head operates on the magnitude and class prediction head operates on the direction. We also estimate the unknown class probability by the prediction confidence, namely the maximum class probability. Secondly, we further enforce orthogonality in the prediction space by minimizing the linear correlation between objectness and class predictions according to the following objective of squared correlation coefficient. As can be seen in the figures below, this objective largely mitigates the linear correlation between objectness and class predictions. Lastly, during incremental learning of new object classes, the previously mentioned feature orthogonality may be compromised, as the object features are no longer distributed over a hypersphere. To mitigate this representation shift, we calibrate feature orthogonality with a task-specific affine transformation, where the task identifier is sampled from the following task probabilities. As can be seen on the right, the feature orthogonality is better preserved as the singular values of object features becomes more uniform, indicating that it looks more like a hypersphere. Next, let's look at the experiments. We first validate our method on two open-world object detection benchmarks, where it consistently achieves state-of-the-art unknown class recall and yields significant improvement on non-class MAP as well. It also proves effective in the incremental object detection task, where it achieves state-of-the-art MAP with over 2% improvements. Lastly, in the qualitative comparison with the previous leading method, Randbox, our method demonstrates better unknown class detections, as evidenced by the kite in the first image, and also less confusion between non-classes and unknown classes, as evidenced by the bed in the last figure. If you are interested in our work, please visit the following link for our public released code. That's all. Thank you for listening.